Welcome to Ask and Learn.
We are going to determine the set of points at which the following function is continuous. Function is defined as f of xy equals x squared times y cubed in the numerator over 2x squared plus y squared, and that for all points different from the origin 0, 0, and at 0, 0 the function is defined as 1. So we are going to talk about where this function can be continuous. And we see that we have a fraction as the main definition of the function, and the denominator 2x squared plus y squared is greater than or equal to 0 for all x and y in the plane R2. And that's because we have squares and a positive constant 2, so all the expression is positive or 0. In fact, because the two terms we are adding are both non-negative, the only way that the sum can be 0 is that both terms are equal to 0. And because 2 is not 0, that means that x squared and y squared must be equal to 0, both, and that means that x and y are both equal to 0. So 2x squared plus y squared is equal to 0 if and only if x equal y equals 0. It means that the fraction x cubed times y cubed over 2x squared plus y squared is well defined at all points different from the origin. So when we take the limit when xy approaches or goes to pair x0 y0, we can say that this is equal to the evaluation of the function at that point if the point we are talking about is not the origin. That is, we are sure that the limit coincides or is equal to the value of the function because we have a well-defined function at all the points different from the origin. So we can evaluate the function at the value where x and y is convergent. And then the only point where the function can be discontinuous, if it is at all, is the origin. So the only possible point of discontinuity for f is 0, 0. But in fact, we are going to see that the limit at 0, 0 is 0. And the function is discontinuous because it has been defined as equal to 1 at 0, 0. In that case, we know that if we define the function at 0 at the origin, then the function will become continuous. But as it's defined just this way, if we prove that the limit of the function when xy converges to 0 is 0, then the function will be discontinuous only at the origin. So let's see that the limit when x and y goes to 0, 0 of the function f of xy is equal to 0. And to see that, we use polar coordinates. We know that any point in the plane can be written in polar coordinates. In fact, the point is different from 0, 0 because we are approaching 0, 0. It doesn't matter. Or even we don't want xy to be equal to 0, 0. So we symbolic coordinates x equal to r cosine of an angle phi and y equals r sine of phi. And with this we describe, as we said, all points in the plane. And we have that limit when xy goes to 0, 0 is equal to, or becomes the limit when r goes to 0. Look here that sufficient to go to 0 at the radius, because with that we are approaching from all directions. So it doesn't matter the angle, but the important thing is that the radius goes to 0. So this limit is the same as saying that the radius is going to 0 of the expression f at r cosine of phi r sine of phi. That is, we gotta replace r x by r cosine of phi and y by r sine of phi in the definition of f, because we are all time in points different from the origin. We use the expression defining f in all points except the origin, that is the quotient x squared y cubed in the numerator, that is the limit when r goes to 0 of this expression squared, that is r squared cosine squared phi, times y cubed, that is r cubed sine cube of phi, over 2x squared, that is r squared cosine squared phi, plus y squared, that is sine square of phi. And this is equal to the limit when r goes to 0. And look here that we have r squared in the denominator as, I forgot, as r squared, in fact, here, because we have y equals r sine phi. So we have r squared sine square phi. So what I was saying is that we have r squared in the denominator as a common factor. We get it out and can simplify with this r squared here. So in the numerator, we stay with r cubed cosine square of phi times sine cube of phi over 2 cosine square of phi plus sine square of phi. And in the numerator, we have r cubed cosine square of phi times sine cube of phi. In the denominator, we can do something. 2 cosine square of phi, we write it as cosine square of phi plus cosine square of phi, the same thing, plus sine square of phi. And with that, we identify this sum here equal to 1. So this is equal to the limit when r goes to 0 of r cubed cosine square of phi sine cube of phi over 1 plus cosine square of phi. And because cosine square of phi is greater than or equal to 0, when we add 1, that value in the denominator is strictly positive. It never equals 0. So for every phi is different from 0, so this limit is exactly equal to 0, because in the numerator we have r cubed times a value, and so that goes to 0, and the denominator is different from 0. So we can try to be a little more, express a little more. The idea is that we have 0 as limit in the numerator, and the denominator we don't have r, so it's 1 plus cosine square phi. And here we say 1 plus cosine square phi is positive, strictly positive for any phi, and so this is 0. Certainly we could do this by using the Cartesian coordinates, but it's easier this way. So we have proved that limit when xy go to 0, 0 of f is 0, which is different from the image of 0, 0 that has been defined, which is 1. Then f is discontinuous at the origin. And so because we were at the set of point in which the function is continuous, is the whole plane minus the origin. So the set where f is continuous is R2, the whole plane, minus the origin, because this is the only point where the function is discontinuous. If we graph the function, it's very interesting that I haven't done that, but I haven't printed out the result. You can see that the function is, you have very beautiful curvatures all around, but at the origin, near the origin, the function is very flat. So it's a very beautiful draw here. You can do it in your calculator or CAS in order to see the idea. But then we have, this is the set of continuity of the function, that is the whole plane minus the origin, and that's the same as saying that the function is discontinuous only at the origin. And that's the final result here.